Hello, everyone, and welcome back to our series on the theory and algorithms of knowledge tracing. Today, we're diving into two fundamental and incredibly powerful algorithms: collaborative filtering, or CF, and probabilistic matrix factorization, or PMF. If you've ever wondered how Netflix seems to read your mind with movie recommendations, or how an app can suggest the perfect next question for you to practice, this video is for you. We're going to break down these concepts step by step using a simple example so you can truly understand how they work. Let's get started. Let's start with a simple analogy we can all relate to: Netflix. How does Netflix know what to recommend? It doesn't have a magical way to read your mind. Instead, it looks at your behavior, your viewing and rating history. It finds patterns among millions of users. For instance, it notices that a huge number of people who loved Interstellar also loved Inception. So, if you loved Interstellar, it's a good bet you'll enjoy Inception too. Now, apply this idea to education. This is exactly what CF and PMF do in knowledge tracing. The system doesn't need to know the true ability of a student. It just looks at their interaction log, what problems they've solved, and whether they got them right or wrong. It then finds patterns in this data. The core idea is brilliant in its simplicity. Focus on the interactions, not the individual. To understand how these algorithms work, we need to get familiar with a few key terms. First, the user item matrix. Think of this as a big spreadsheet. Each row is a student, each column is a question, and the cell tells us if the student got that question right, wrong, or didn't attempt it. Next, latent factors or latent vectors. This is the magic sauce. We represent each student and each question as a vector in a hidden mathematical space. Matrix factorization is the process of taking that big matrix and breaking it down into the product of two smaller matrices of these latent vectors. Similarity is just a measure of how close two vectors are. Finally, a neighborhood is just a fancy term for the people most like you. So, we have two main approaches: CF and PMF. What's the difference? Collaborative filtering, CF, is the classic approach. Its core idea is to find your neighbors, people who have interacted with the system in a way that's similar to you, and use their behavior to predict yours. Probabilistic matrix factorization, PMF, takes a different route. It's a model-based approach. Instead of just looking at your neighbors, PMF first tries to learn a fundamental model of how the entire system works by finding those latent vectors we talked about. The key takeaway is that CF is like asking your friends for advice, while PMF is like building a sophisticated AI that understands the underlying patterns of taste and ability for everyone. All right, let's roll up our sleeves and do some actual calculations. Here's our scenario. We have 5 students and 4 questions. The first 2 questions are about linear equations, and the last 2 are about quadratic equations. We have their answer records, marked as 1 for correct, 0 for incorrect, and a question mark if they didn't attempt it. Our goal is to predict the probability that Xiao Ming will get question 3, a quadratic equation problem, correct? First, let's try user-based collaborative filtering. The idea is simple. Find students who are like Xiao Ming and see what they did on question 3. To find like students, we use a mathematical measure called cosine similarity. Let's calculate the similarity between Xiao Ming and Xiao Hong. They both attempted questions 1 and 2. Plugging their scores into the formula gives us approximately 0.707. Now, let's compare Xiao Ming with Xiao Li. They also both did questions 1 and 2. The calculation gives us a perfect score of 1.0. This means their answer patterns are identical for the questions they've both attempted. Now we have our similarity scores. We see that Xiao Hong and Xiao Li are the most similar to Xiao Ming, and importantly, they both attempted question 3. Xiaohong got it right, and Xiaoli also got it right. The next step is to combine this information using a weighted average. We multiply each neighbor's score on question 3 by their similarity to Xiaoming, sum those products, and then divide by the sum of the similarities. Plugging in the numbers, we get 0.707 by 1 plus 1.00 by 1, divided by 0.707 plus 1.0000. This simplifies to 1.707 divided by 1.707, which equals 1.0. So, user-based CF predicts that Xiaoming has a 100% chance of getting question 3 right. Now let's try the other flavor of CF, item-based. Instead of looking for similar students, we look for similar questions. The logic is, if question A is similar to question B, and a student did well on A, they are likely to do well on B. We use the same cosine similarity formula, but this time we apply it to the columns, questions, of our matrix. Let's find the similarity between our target question Q3 and the question Xiaoming has already answered, Q1 and Q2. Calculating the similarity between Q1 and Q3 gives us a perfect score of 1.0. The similarity between Q2 and Q3 is approximately 0.707. This means Q1 is considered identical in pattern to Q3 based on the data we have. Now for the prediction step. We know how similar Q1 and Q2 are to Q3, and we know how Xiaoming performed on Q1 and Q2. He got both right. We use the same weighted average formula again. We multiply Xiaoming's score on each similar question by the question's similarity to Q3, sum those up, and divide by the sum of the similarities. The calculation is 1.000 by 1 plus 0.707 by 1 divided by 1.000 plus 0.707. Once again, this equals 1.0. So, item-based CF also predicts a 100% chance of success for Xiaoming on question 3. Both methods arrived at the same conclusion through different paths. Probabilistic matrix factorization, PMF, is a classic model-based method in collaborative filtering. Unlike neighborhood-based methods that directly find people similar to you, it assumes that each user and each item can be represented by a low-dimensional latent feature vector. PMF infers these latent vectors from observed user item rating data and then uses them to predict unknown ratings. Simply put, it doesn't memorize who likes what, but rather learns what kind of things users like and what attributes things have. This gives it stronger generalization ability than pure neighborhood methods in cold start scenarios with new users and new items. PMF has a few key parameters that control how the model learns. K is the dimension of the latent vectors. Think of it as the number of hidden features we want the model to discover. Lambda is a regularization term. It's like a safety guard that prevents the model from creating overly complex latent vectors. Squadra, sigma squared, accounts for noise, like when a student knows the answer but clicks the wrong button by accident. The model's goal, defined by its objective function, is to find the U and V matrices that best satisfy two conditions. First, the product U times V should be as close as possible to the real user item matrix R. Second, the vectors in U and V should be as simple as possible. Let's do a simplified calculation for PMF. We'll use the same dataset and set the latent factor dimension k to 2 for simplicity. Here are the two-dimensional vectors for our students and questions. To predict Xiaoming's performance on question 3, we simply take the dot product of his vector and the question's vector. Calculating the dot product, 1.2 by 0.8 plus 1.8 by 0.5 equals 0.96 plus 0.4, which is 1.36. This is our raw matching score. To turn this into a probability between 0 and 1, we apply a function like the logistic function. This gives us approximately 0.794, or a 79.4% chance of getting the question right. Notice that this result is different from the 100% we got from CF, showing how different models can lead to different predictions. You might be wondering, how do we actually find these latent vectors u and v? It's not magic, it's optimization. The two main methods are alternating least squares, ALS, and gradient descent. ALS works by a process of iteration. You start with random guesses for u and v. Then, you hold one matrix constant and solve for the best possible other matrix. You keep switching back and forth until the predictions are as good as they can get. Gradient descent is even more common. It's like walking down a hill blindfolded. You take a step, feel which way is downhill, and take another step. You keep doing this until you reach the bottom. So, why are these models important in the real world? First, they are great at handling the cold start problem. If a new student joins the platform and has only answered a few questions, CF and PMF can still make reasonable predictions. Second, they offer a level of interpretability. It's much easier to explain a recommendation by saying, "Students like you found this helpful," than to try and explain the output of a complex neural network. Third, they are computationally efficient. Now, let's connect this to cutting-edge research, like the Optimal Challenge Zone, OCZ. If a CF-PMF model predicts a success probability between 50% and 70%, that's a strong indicator the task is in the OCZ. Additionally, we can combine these models with other data sources. For example, if eye tracking data shows a student is tired, we can reduce the weight of their answers from that time in the CF model. Let's wrap up by addressing some common questions. First, why go through the trouble of using latent vectors? Because real-world patterns are complex. Latent vectors allow the model to discover hidden connections that aren't obvious from the raw data. Second, how do you choose the right dimension k for the latent vectors? A good starting point is around 50, and then you test different values to see what works best for your data. And finally, the cold start problem. How do you handle a brand new student or a brand new question? For a new student, you can start them off with the average student vector. For a new question, if you have information about it, you can use that to give it a sensible starting vector. So, to recap, collaborative filtering is the intuitive, neighbor-based approach. It's like asking your friends for a recommendation. Probabilistic matrix factorization is the more mathematical, model-based approach. It's like building a sophisticated AI to understand everyone's preferences. So, to recap, collaborative filtering is the intuitive, neighbor-based approach. It's like asking your friends for a recommendation. Probabilistic matrix factorization is the more mathematical, model-based approach. It's like building a sophisticated AI to understand everyone's preferences. Both are incredibly powerful and widely used. They are fundamental tools not just for movie recommendations, but for creating adaptive learning experiences that can truly personalize education for each student. Thank you for watching.